Hello everyone. My name is Ullas K and I am part of Embedded System Internship at Emertxe. As a part of this internship, I had opportunity to work on an exciting project titled Washing Machine Simulation using the PIC 16F8778 microcontroller. In the upcoming slides, I'll walk you through the tools used, system design, components, implementation, and final output of the project. In today's modern world, household appliances have become essential in streamlining daily chores, reducing man labor, and enhancing overall efficiency. Advancement in technology, particularly the integration of microcontrollers, have revolutionized washing machine, now making them smarter, more energy efficient, and user friendly. The washing machine project utilizing the PIC 16F8778 microcontroller emphasizes this innovation by aiming to design an reliable, intelligent, and adaptable washing solution. Features such as automatic water level customizable wash cycles and real-time error notification can now be implemented with ease using microcontroller based systems. Such smart systems not only improve washing performance but also contribute to water and energy conservation, aligning with sustainable living goals. Now let's look into C and embedded C difference. C language is a general purpose high level programming language known for its simplicity, performance, and ability to interact closely with hardware. Its speed, probability, and structured in syntax make it ideal for developing system, software operating systems, and low-level applications. Embedded C. Embedded C is an extension of C language tailored for programming embedded system and microcontrollers. It provides special features such as direct access to hardware registers, input-output ports, and fixed memory locations using specific keywords, allows low-level bit manipulation while maintaining code readability and profitability across different hardware platforms. Widely used in industries like automotive, consumer electronics, robotics, and home automation due to its reliability and deterministic behavior. An embedded system is an integrated combination of hardware and software engineered to carry out a dedicated function with maximum efficiency. These systems are widely used for control, automation, and performance critical applications. Unlike general purpose computers such as PCs or smartphones, embedded systems are designed for specific task or application, highly optimized in terms of performance, cost, power consumption, and physical size. Operate autonomously with minimal or no human interaction. Real time capable, ensuring precise and timely response to inputs commonly used in industries like automotive, healthcare, consumer electronics, and industrial automation. Detection categories of embedded system. Standalone embedded system work independently without a host, accept input, process it, and provide output. Example digital camera, washing machine. Slave standalone embedded system operate under the control of master device. Execute functions only when triggered. Examples LED display units managed by a controller. Independent standalone embedded system. Fully autonomous and self-operating. Handles all operations internally. Example microwave, oven, or electronic toys. Real-time embedded system designed for applications require immediate response to inputs. Hard real-time embedded system. Strict deadlines must always be met. Failures to respond time may lead to system failure. Example medical monitoring system, automotive crash sensor. Home real-time embedded system. Deadlines are important but rare delays are tolerable. Delay may reduce performance but won't cause total failure. Example industrial control systems. Soft real-time embedded systems. Timely response is preferred. but not critical. Occasional delays do not cause major issues. Example, multimedia system, online gaming. Mobile embedded system, designed to function in probable device with limited resources. Emphasizes on low power consumption, compact size, and mobility. Example, smartphones, GPS device, fitness trackers. Hybrid embedded systems combine features of multiple embedded system types. Example, real-time plus networked. Offer greater flexibility, scalability, enhanced functionality. Example, smart vehicles with GPS, real-time braking, and internet connectivity. Microcontroller based washing machine stimulation using PIC sim lab. What is the purpose of the project? The project simulates a washing machine using PIC sim lab, a virtual environment for embedded system testing, aimed to replicate real-world washing machine functionality for learning and testing purpose. Begins with a thorough understanding of washing machine hardware components, operational cycles, key laundry parameters, fabric type, load size, water level. These parameters are used to define and control the washing process within the simulation. MPLab X IDE. MPLab X Integrated Development Environment is a flexible and a user-friendly platform developed by Microchip, used to configure, develop, and debug embedded applications. Support a wide range of PIC microcontrollers and digital signal controllers, compatible with Windows, macros, and Linux. XC8 compiler. AC compiler provided by Microchip for 8-bit PIC microcontroller. Translates C source code into machine-level code for execution. Support Windows, Mac OS, and Linux environments. Generates optimized, efficient code for embedded application. IC Sim Lab stands for Programmable IC Simulator Laboratory, a real-time simulator for embedded development boards. Allows testing of embedded code without physical hardware. Integrates with MPLabX debugger for complete virtual development and debugging. Now let's look into the PIC 16F877A microcontroller. Type 8-bit microcontroller from the PIC family by Microchip Technology. Memory, programmable memory, 14 KB flash. Data memory, 368 bytes RAM. Clock and power, built-in internal oscillator and supports low power modes. Operational voltage, typically 5 volts. Development tools supported by Microchip compiler, IDEs, and debugging tools. Compatible with XE8 compiler for efficient C programming. Now, let's look into the components used. Tactical switches. In microcontroller, switches are often used as inputs to control the operation of device or to interact with the user. When the button is pressed, the switch turns on, and when the button is released, the switch turns off. An array of tactical switches from digital keypads. Here, RB3 is used as switch for navigation between options. RB4 is used as switch 5, powering on washing machine and resume. RB5 is used as switch 6, stop and pause the ongoing program. RB0 is used as switch to indicate door status of washing machine. CLCD, Character LCD Display. CLCD stands for Character Liquid Crystal Display, commonly used in embedded systems. It is an alphanumeric display module capable of showing both letters and numbers, typically configured in 4 rows, with each row displaying up to 16 characters. Supports communication in both 8-bit and 4-bit modes, depending on system requirement. In this project, the CLCD is used to display the current status of washing machine, example, wash cycle, time remaining, or errors. Keypad interface. Keypads are used as input device to send user commands in binary format, composed of push button arranged in a matrix layout, used to select functions, enter values, or control operation in embedded system. Triggering methods. Level trigger. Activate when a constant high voltage level is detected. Edge trigger. Activate by a sudden change in voltage level. Circuit configuration. Sourcing circuit. Logic 1 on, logic 0 off. Syncing circuit. Logic 1 off, logic 0 on. Timers in PIC 16F877A. A timer is essentially a binary counter that counts clock pulses, internal or external. When the counter reaches its maximum value, it sets to 0, sets an overflow flag, and can generate an output if enabled. Timers are commonly used for delays, event counting, PWM generation. The microcontroller includes three independent timers: timer 0, 8-bit, timer 1, 16-bit, timer 2, 8-bit timer also used for PWM, pulse width modulation generation. Interrupts in embedded system. An interrupt is a mechanism that temporarily halts the processor's current task to handle a higher priority event or signal. Once the interrupt is served, the processor resumes its previous task. Types of interrupt: external and internal. External triggered by external device or signals, example keypad or sensors. Internal generated by internal peripherals, example timers, ADC, UART. Interrupt service routine, a special software routine automatically executed when interrupt occurs. The ISR identifies the interrupt source, processes it, and returns control to the main program. In PIC microcontroller, a single ISR is used to handle all enabled interrupts. Buzzers. The buzzers is used to indicate the completion of washing cycle. It is activated for 2 seconds once the washing process finishes successfully. Helps the user keep track of the machine status without constant monitoring. Fan. The fan is used to stimulate the washing machine motor in the project. It starts spinning when any wash mode is selected. The fan continues running throughout the wash cycle. Safety features. The fan stops automatically if the door is open, resumes operation when the door is closed. The block diagram. Switch 1 shows the door status, whether the door is open or closed. Switch 4 helps us navigating through the washing machine display. Switch 5 tells us about the helps us to switch on the washing machine. Switch 6 helps us to play and pause the washing machine. The operation can be seen in the display. The buzzer will turn on when the washing machine has completed its operation. Now let's look into project demo. Conclusion: this project successfully showcases the design and simulation of a washing machine using the PIC16F8778 microcontroller. Core embedded system concepts were effectively implemented to control real-time operations using timers and interrupts. Interface peripherals devices such as the keypad, PLCD buzzer, and fan delivers a user-friendly experience with mode selection, water level control, and status feedback. Thank you. I would like to sincerely thank Emertxe for providing me the valuable opportunity to participate in the online internship on embedded systems. This internship has greatly enhanced my understanding of embedded system design, programming, and real-time application development. I'm truly grateful for the guidance, resources, and the support offered throughout the program. Thank you once again for this enriching learning experience.